Have you ever wondered, what if time could flow backwards? Let's take a journey through the complex labyrinth of space-time. For centuries, humanity's understanding of these two elements has been in constant evolution. Our ancestors, the earliest philosophers and astronomers, saw space and time as two separate entities. Space was the vast expanse around us, the canvas upon which the universe painted its celestial bodies. Time, on the other hand, was viewed as a relentless river, flowing in one direction, carrying everything in its path. But then, Sir Isaac Newton came along and turned our understanding on its head. He proposed the concept of absolute space and time. In Newton's universe, space was an unchanging, infinite container, unaffected by what was inside it. Time, too, was absolute, ticking away at the same rate, regardless of where you were or how fast you were moving. Yet this was not the end of the story. In the early 20th century, a certain Albert Einstein had a revolutionary idea. He introduced us to the concept of space-time, a four-dimensional fabric that weaves the universe together. No longer were space and time separate entities. They were intertwined, interconnected. They were two sides of the same coin. In Einstein's universe, space and time were not absolute. They were relative, bending and warping under the weight of mass and the speed of light. This was a dramatic shift from Newton's rigid universe. It opened up a whole new world of black holes, gravitational waves, and time dilation. From separate entities to a combined fabric, our understanding of space and time has taken quite a turn. But the journey doesn't end here. Imagine a balloon expanding. Now think of the universe in the same way. In the early 20th century, our understanding of the universe took a dramatic turn. It was then that astronomer Edwin Hubble made a groundbreaking observation. He noticed a peculiar phenomenon. The light from distant galaxies was redshifted. But what does this mean? Well, when light waves stretch, they move towards the red end of the spectrum, hence the term redshift. This indicated that the galaxies were moving away from us. This was a startling revelation. If galaxies were moving away from each other, it meant that the universe was not static, as previously thought, but was expanding. This was akin to blowing up a balloon. As the balloon expands, the dots marked on its surface move away from each other, just like galaxies in our universe. But here's the twist. It wasn't just that galaxies were moving through space, rather, space itself was expanding. This was a radical shift in our understanding of the universe. In a static universe, space is a rigid stage where events play out. But in an expanding universe, space becomes a dynamic player. It stretches, it morphs, it plays an active role in the cosmic drama. This idea added a whole new dimension to our comprehension of space-time. Time was no longer a steady river flowing at a constant pace. It was now part of a four-dimensional fabric called space-time, which was flexible and ever-changing. The discovery of the expansion of the universe had profound implications. It implied that our universe had a beginning, a moment of creation. It also suggested a future where galaxies would drift further apart, stars would burn out, and the universe would grow cold and dark. This was a monumental shift in our understanding of our place in the cosmos. We went from seeing ourselves in a static, eternal universe to realizing we are part of a dynamic, evolving cosmos. As space stretches, so does our understanding of the universe. But there's more to this tale. What if time passed slower for you than for your friends? Sounds like science fiction, right? But what if I told you that this idea is a cornerstone of one of the most groundbreaking theories in physics? Enter Albert Einstein and his theory of relativity. This isn't just about E equals mc squared. It's about the very nature of time and space. According to Einstein, time is not a constant. It can slow down or speed up depending on how fast you're moving relative to something else. This is not a mere hypothesis, but a well-documented phenomenon known as time dilation. So let's put on our thinking caps and dive into the world of relativity. Imagine you have a twin. You're both the same age, but while you stay on Earth, your twin embarks on a journey into space at near light speed. According to Einstein's theory of relativity, when your twin returns, they'd be younger than you. This is known as the twin paradox. The paradox lies in the fact that each twin sees the other twin as moving, so each should paradoxically find the other to be younger. But this is resolved in the theory of relativity by understanding that the twin traveling had to accelerate and decelerate, which breaks the symmetry. Just think about it. Your twin went on a space journey and came back younger than you. It's not because of a miraculous space-age moisturizer. It's because time itself moved slower for them. In the realm of the superfast and the supermassive, time becomes a flexible fabric rather than a steady, unchanging river. It's like a cosmic magic trick, where the universe itself is the magician, and we're still trying to figure out how the trick works. This concept might seem a bit mind-boggling, but that's the beauty of science. It constantly challenges our understanding of the universe, pushing the boundaries of the known into the unknown. Next time you're running late, just remember, according to Einstein, you're actually stretching time. Ready for a trip down the rabbit hole of quantum mechanics? Let's dive into the fascinating realm of the infinitesimally small, where the familiar laws of physics are turned on their heads. Quantum mechanics, a field that has baffled and intrigued the brightest minds for over a century, takes us into a world that defies our everyday intuition. The cornerstone of this quantum world is Heisenberg's uncertainty principle. It's a fundamental concept that tells us something quite strange. We cannot precisely know both the position and the momentum of a particle at the same time. You might be thinking, wait, isn't that odd? Yes, it is. And it's a departure from the deterministic laws that govern the larger classical world we inhabit. But why is this so? Well, it's not due to any limitations in our measuring tools or techniques. Rather, it's a fundamental aspect of nature itself. In the quantum realm, particles behave like waves, and these waves spread out over space. The more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. So, what does this mean? Imagine you're trying to pinpoint a tiny particle in a dark room. The more accurately you try to determine its location, the less you know about how fast it's moving or in what direction. This is the crux of the uncertainty principle. This principle isn't just a theoretical curiosity. It's foundational to the structure of atoms and the stability of matter. Without the uncertainty principle, electrons could spiral into atomic nuclei, collapsing matter as we know it. So in a very real sense, the uncertainty principle is a key player in the cosmic drama that allows life to exist. Quantum mechanics, with its inherent uncertainty, paints a picture of a universe that is less like a well-oiled machine and more like a vibrant dance of probabilities. It's a world where particles can be in multiple places at once, pass through impenetrable barriers, and get entangled over vast distances. Quantum mechanics shows us that at the smallest scales, space and time become fuzzy and uncertain. So, where does this leave us in our understanding of space-time? Well, the field of theoretical physics is still brimming with questions, and scientists are constantly pushing the boundaries of what we know. In our quest to reconcile the theories of relativity and quantum mechanics, some intriguing ideas have emerged. One such idea is string theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional objects called strings. In string theory, space-time is a fabric woven by these strings, vibrating at different frequencies to create the particles we observe. This theory is still in its infancy, but it has the potential to provide a unified description of gravity and particle physics, a long-held ambition in the scientific community. Meanwhile, another fascinating area of research is quantum gravity, a theoretical perspective that seeks to describe gravity according to the principles of quantum mechanics. Quantum gravity aims to resolve the discrepancies between quantum mechanics and general relativity, providing a more comprehensive understanding of the nature of space-time. While still hypothetical, quantum gravity could lead to groundbreaking discoveries about the fundamental structures of the universe. One of the most exciting aspects of these theories is that they could open up entirely new dimensions of space-time. Imagine, if you will, A universe where there are more than just the four dimensions we're familiar with. This is not mere speculation, but a serious proposition in string theory and other quantum gravity models. As we delve deeper into these theories, we may find that our understanding of space-time is far from complete. We may discover that space-time is more complex, more beautiful, and more mysterious than we ever imagined. As we continue to explore the mysteries of the universe, who knows what new insights await us in the realm of space-time. The future of space-time is a thrilling frontier, and we stand on the brink of potentially transformative discoveries. Here's to the journey ahead.